Welcome. In this session, we'll define the dual formulation, which is a different way of looking at the Lagrange function. What we'll do from the previous session is we'll extend a property function being equal to 0 to a set of property functions being all equal to 0, and specifically we'll extend this idea of a one form times an argument minus a constant. That will be extended to the way we can write this is we can write that is if there's a vector of Lagrange multipliers and a matrix that is constraining and a vector that is constraining. So let's keep that in mind. So in this, if we take that extension, the Lagrange function for an objective that has a vector argument, and now we'll have more than one Lagrange multiplier, is the objective function plus the transpose of the multiplier vector times the constraint matrix minus the constraint vector. So that's the extension of the Lagrange function to having more than, where this matrix M now has more than one row, and so for each row we get a multiplier, and that's how we get numerous multipliers. So what we want to do is we want to find, for this, now we want to find an optimal argument and an optimal set of Lagrange multipliers that are the result of minimizing, instead of minimizing the objective, now we're going to try to minimize the Lagrange function. And so this will range over all vectors that are in that vector space, and also there will be up to L, say, Lagrange multipliers. The way that we might approach this, if we were looking at a feasible set method, is we might say, well, can we eliminate these multipliers and make this just a minimization over the vector space? And that would turn it into an unconstrained optimization problem. There's another way. So let's consider this idea, is instead of trying to eliminate the multipliers, can we eliminate the vector argument from the Lagrange function? So this is some, let's call it some g, and that g will now depend only on the Lagrange multipliers. When we were exploring the differential equation that led to the Lagrange function, we said there were an infinite number. And here, again, there are an infinite number of ways to eliminate the w. Of them, one is referred to as the dual formulation. So the dual formulation is this. Is what we do is we will consider a function only of the Lagrange multipliers, and we'll say that results from, how do we eliminate w? Well, let's try minimizing it. So from minimizing the Lagrange function for the vector argument. So does this work in general? Well, it's not clear that it would work in general, but it sure works for this kind of constraint that we have. It works for these linear equality constraints. So we'll define this. It's usually written as a script L with a subscript D, and now its argument is only the Lagrange multipliers, and that is defined as the argmin over all vectors in the vector space of the primal Lagrange function that has the vector argument and the Lagrange multipliers as its argument. So this is that function g, is of the infinite number of g, we're going to pick the one that is the result of an argmin process. So this is non-intuitive, and I'll just say see the notes, and the notes will then refer you to, there are many good proofs. The one that I particularly like is in the text by Boyd and Vandenberg. You can probably find others. So non-intuitive, see notes, and this is, I'll emphasize this, is even for a non-convex objective function, the dual function that has the Lagrange multipliers as its argument is concave. And that means that it's the negative of it is convex. So as I said, this is not intuitive, but it is something that comes out when we follow through this argmin process. Now, let's use that concave property to write our optimization a little more carefully. So we know that the dual is concave. And that means we could write our problem this way. So let's consider the minimization. That is, let's not look at the argmin. Let's look for a moment at the very closely related min. So the min, the minimum over all vectors in the vector space and all possible Lagrange multipliers of the Lagrange function that has the vector argument and the Lagrange multipliers, we can now write that this way. We can say that that is the minimum over all vectors in the vector space. And because the w's and the mu's, that is the vector and the multipliers, are independent of each other, they're in different vector spaces, so they're really independent of each other. Because they're independent of each other, we could break this down into two min problems. Except they're not exactly min problems, right? Because this is concave, that means that solving this min is actually solving a max problem, right? That if a function is convex, we're looking for a min. If a function is concave, we're looking for a max. So that's the minimum of the vectors and the maximum of the Lagrange multipliers of that primal Lagrange function. So let's write this down. Because w and mu are independent, they commute. And that means that we can write this minimization, so we can say that the minimum value over all vectors in the vector space and all possible Lagrange multipliers, the minimum value, the minimum level that the Lagrange function can take, I could rewrite that as the max of the Lagrange multipliers of the min of the vectors in the vector space of the primal Lagrange function that has a vector argument and takes in all the multipliers. Well, we have a symbol for this part, right? That this minimization was how we defined the dual. So that is the maximum over of the Lagrange multipliers of the dual problem, and now we've eliminated that W, and this is only referring to the mu. So what we've done in this is, if we look at this dual, we have changed a big, huge dimensional optimization problem into one that's much smaller. For example, if there are only two constraints, then there are only two Lagrange multipliers to find. Now, the whole trick in this is, what about this, the definition of the Lagrange dual, right? We said that that was the minimum. We had to do a minimization. Well, that minimization, if our Lagrange function has certain simple forms, we can write that minimization in a closed form. So that's what we're going to do in a subsequent session.